So let's make sure we're good with the idea that a source charge makes an electric field, and let's figure out how we're going to find the expression for that electric field. To first make sure we understand the concept, we're going to go back to our analogy with gravity. So if we have the Earth, how would we find the gravitational field G at some point around the Earth? And this is probably something you did in physics 1050 or 1020, but maybe just never developed it this way. So let's say we point at an empty spot in space. So nothing here, we're just pointing at it. What is G at that point? Well, our first step in that process is let's put an apple at point P. So what if we had our Earth right here and we put a little apple at point P? What would be the force due to gravity on that apple? Well, we know that the force would point straight down, and we call that the force due to gravity, or the weight. So let's draw that force vector in. There are two ways to write down the force due to gravity that's acting on the apple. First, we can use Newton's law of universal gravitation, which would be G times the mass of the Earth times the mass of the apple, divided by the distance between the Earth and the apple squared. Okay, so that's one way we would write down the force due to gravity. The other, more familiar way, is just to say m times g. We know that the direction of our force is towards the center of the Earth. So let's put all this together and solve for g. What we see is that our masses of our apple cancel, and we're left with a vector g equals our constant of universal gravitation times the mass of the Earth divided by the distance squared, and the direction for G is towards the center. Okay, so we found an expression for our gravitational field G, and this is true with or without that apple. There doesn't need to be anything at that point in space in order for G to exist. Okay, we're going to take this idea and we're going to do it with electric field. All right, let's use that same process again, and let's find the electric field at some point P near a source charge Q. Let's get our labels in. So this gray dot represents point P. It's an empty point in space. There is nothing there. So P is just an empty point in space. We're just pointing at it, that's all. And then our source charge drawn in pink here is Q. We've got a positive source charge here. It doesn't have to be positive, but we'll start with positive. We'll talk about negatives later. Okay, what's next? So the next way to sort this out is let's put a positive test charge close to our source charge. So there's a little plus because it's a positive test charge, and I'm going to label it with a lowercase q. So Q is my test charge. It's small and positive, and it's placed at point P. Okay, so our next step is let's measure the force on our small positive test charge. Well, our source charge is positive, our test charge is positive, so we know the force between those two things is going to be repulsive. So it's going to point directly away. So there's my electric force on my test charge or my probe charge, little q. So I'll draw in my electric force vector up here. What can I say about that electric force vector? Well, my force vector has a magnitude of Coulomb's constant K times the magnitude of our source charge times the magnitude of our test charge divided by the distance between their centers squared. Put that in my diagram next. Okay, so that's the magnitude of the force. The direction of the force, because force, of course, is a vector. So the direction, I think I'll write away from Q. You could also write repulsive, but let's stick with away from Q for right now. So now the next step in our process is let's remove our test charge Q and see what's left. So we've still got our source charge, and now we've just got our empty point in space. Remember, there's nothing at point P, it's just a spot in space that we're talking about. And let's ask what's left over. Well, we know that electric field is force per unit charge. So it's the force divided by the test charge. That means the magnitude of our electric field is equal to the magnitude of our force divided by the magnitude of our test charge Q. So that gives us that the magnitude of our electric field E is the magnitude of our force, K times source charge times test charge divided by R squared, and that's all divided by the magnitude of the test charge. That gives us the result of our test charges cancel. And actually, I'd like to write this bigger, so I think I'm just going to come up here. The magnitude of our electric field is equal to K times the magnitude of the source charge divided by R squared. We'll label in R again just to make sure we don't forget. Electric field, of course, is a vector. We have that our electric force points away from our source charge, so points away from the source charge. Our test charge is positive, so that we know electric force and electric field are in the same direction. I'm going to go ahead and draw my electric field. Electric field must be in the same direction as my electric force because my test charge is positive. So the direction of my electric field is away from Q. Okay, hopefully that clarifies how to calculate our electric field around a point charge. So we do our Coulomb's constant K times the magnitude of the point charge divided by the distance between our charge and the point we're talking about, and that distance has to be squared. Now, electric field is a vector, as is the force. Right now I've just written the direction by saying away from Q. Let's clarify that direction a little bit better with a unit vector notation. People who really like math might really like this notation. So if we'd like to write our electric field in unit vector notation, let's first remember what our unit vector notation means. So I, J, and K are the unit vectors that correspond to the X, Y, and Z directions. If you're coming from Physics 1020 or 1021, you might be used to X hat, Y hat, and Z hat. 1050 and 1051, we use I, J, and K instead of X, Y, and Z. And what a unit vector is, it's a vector of length 1 that points in that direction. So I hat is a vector with length 1 that points to the right. K hat is a unit vector, so it has length 1 and it points out of the page. So we're going to define a new unit vector because up and down, left and right don't really correspond to electric fields. Our electric field in this problem pointed away in this direction. It's related to the source charge. So we need a new kind of unit vector. We're going to define a polar unit vector, r hat. So r hat is a unit vector that points away from Q. Okay, so let's draw that in our picture. Here's our source charge Q. Here's our point P. R, remember, was the distance between the centers of Q and P, so that's R. R hat is the unit vector that points away from Q. So it has length 1 and it just goes straight away. So that's what R hat looks like. Let's remember our electric field vector at point P that pointed away from Q. So if we wanted to write our electric field vector, our electric field would have the magnitude of electric field in the r hat direction. Okay, so let's move down a little bit and let's write that down. So for our electric field vector, we're going to write E is equal to K, and E is a vector, times Q over R squared with an R hat direction. Now, notice here, I did not put a magnitude sign on my charge Q. If you're using this notation, you need to include the sign of charge. And what we'll see, we already looked at the positive charge, we'll look at the negative on the next slide. If our charge is positive, which is what the previous slide was, our result is that our electric field points away from the charge. And if our charge is negative, our electric field vector will point towards the charge. So let's super quick run through what happens if our source charge is negative. So our blue dot shows our source charge Q, it's less than 0. Our little gray dot shows our point P in space. Let's find the electric field vector at point P. We'll start by putting a positive test charge Q at point P, and we'll ask what is the electric force on that positive test charge? Well, we know it has magnitude of K Coulomb's constant times the magnitude of the source charge times the magnitude of the test charge divided by the distance between their centers squared. Let's label that guy. Okay, that's the magnitude of the force. The direction of the force, since our test charge is positive, our source charge is negative, the force is going to be attractive. So let's draw in the electric force. There's our electric force. So our electric force vector, if we wanted to put a direction on it, that force is towards the source charge. Then for our electric field, we know that the magnitude of our electric field is equal to the magnitude of the electric force divided by the magnitude of the test charge. That's going to give us K times the magnitude of the source charge divided by R squared. That's the magnitude. What about as a direction? Well, our test charge is positive. Therefore, the electric force and the electric field are in the same direction. So our electric field vector E is our electric force, our electric force vector. So our electric field vector E is our electric force vector divided by the test charge itself. The test charge is positive, so our electric field then would have a magnitude of K times Q over R squared with a direction of towards the source charge. And we could just as well write that in our unit vector notation, where E is equal to K times Q over R squared times R hat. R hat, remember, is our unit vector that points away from the charge. So there's R hat. If we put a negative Q in here, then our direction for electric field would be minus R hat. Otherwise, in other words, in towards the source charge. So whichever way you prefer to write it is okay. Once we hit magnetic fields, we'll use this radial unit vector notation more often. Let's go back to my favorite example. Let's look at the hydrogen atom. In the hydrogen atom, a proton creates an electric field. We'd like to find the electric field at the position of the electron. So in this setup, the electron then is what we call our test charge or probe charge. And the proton is the source charge. The proton is the thing making the electric field that we're trying to calculate. So if you started to wonder, hey, what about the electron? You might argue that the electron makes an electric field, and I would agree with you. The electron is a charged particle. It does make an electric field, but this problem, however, only asks about the electric field due to the proton. That's why we're not calculating the electric field due to the electron. Okay, let's use our method of calculating electric field. You can either go with the unit vector notation or you can go with magnitude and direction. I think I'll go with magnitude and direction. The magnitude of my electric field is Coulomb's constant K times the magnitude of my source charge, QP, divided by the distance between them squared. So the distance between the electron and a proton in a hydrogen atom is about 53 picometers, where a picometer is times 10 to the minus 12 meters. So K is 8.99 times 10 to the 9 newtons meters squared over Coulomb squared. The magnitude of the charge on my proton is 1.6 times 10 to the minus 19 coulombs. Divide that by the distance squared, 53 times 10 to the minus 12 meters squared, and I get the magnitude of my electric field as 5.12 times 10 to the 11 newtons per coulomb. That's the magnitude. It is very large. This is a big electric field. To write my electric field as a vector, I need to include the direction. And since our source charge is positive, because the proton is the source charge, I know that the electric field will go away from the positive test charge. So the direction is away. You could also write radially outwards. That would be acceptable. Or you could use your unit vector notation, also acceptable. One last note about this problem. You might recall that in a previous example, we found the electric force between the electron and the proton. For this example, you could calculate the electric field from doing our previous force divided by the test charge again. That method would work, and in fact, maybe you'd want to try that as a homework problem just to verify that you get the same answer.